There we go. So what we're going to be looking at today are similar triangles. We're looking at similar and congruent. And the idea of similar triangles is basically this. It's the same shape, different sizes. So same shape, different sizes. Here, I'm going to grab a different pen. There. Now, the idea with this, we're going to get this thing called corresponding sides. So let's say we have a triangle like this. Another one like this. So let's say we have the exact same type of triangle, except they're different sizes. So this is, if you shrunk this triangle, you would get this one. So let's say we have some different sides. So we could call this a base. Let's call this base 1, base 2. This is the back of the triangle, so we could call this back 2 and triangle 2. This would be back 1 for triangle 1. Call this 2 and this 1. And this would be incline 1. This would be incline 2. So we talk about corresponding sides. This is what we're getting at. The inclines, we're going to call those corresponding sides. The backs, those are also corresponding sides. And the bases, they're also corresponding. So when we talk about corresponding sides, that's what we mean. So base to base, back to back, incline to incline. Now, there's some special properties with similar triangles. And again, this is only the case when they're the same shape, but merely different sizes. And so here's a special property. The ratios of corresponding sides are equal. So the ratios of corresponding sides are equal. So, for example, if we take the length of base 2 and divide by the length of base 1, we're going to get the same number if we took back 2 divided by back 1. And that'll be the same number. We took incline 2 divided by incline 1. And one thing you want to keep in mind, I've decided to have the second triangle always on the top and then the smaller triangle always on the bottom. We could flip it. We could do first triangle and then second triangle. That's okay too. What we want to be careful of, we don't want to do second triangle, first triangle, and then do first triangle, second triangle. Then our numbers won't match up. So we want to be careful. We want to be consistent. If we decide to have the second triangle in the numerator, it needs to always be in the numerator for a particular triangle. If we decide to always have the first triangle in the numerator, then we need to make sure it's in the numerator. All right. So the ratios of corresponding sides are equal. Also, the ratios of corresponding heights these are also equal. One thing, add one little bit. The ratios of corresponding heights are equal to the ratios of corresponding sides. So let's say that's height 1. And that's going to be height 2. So we can add this little bit in here. That the ratios of the corresponding sides are equal to the ratios of the corresponding heights. So any questions about that? So that's the major property for similar triangles. So what we're going to do, we're going to take a look at just some examples here. Probably some of the more sort of canonical ones that they have. So I'm going to pick some problems out of the homework. Let's see. All right. You want to find the ratio of the lengths of the corresponding sides of similar triangles. Now, I got to tell you the triangles are similar. So let's say we have this. So what we can do, we want to identify corresponding sides. So right away, we can see we have inclines that have no measure. Well, that's okay. We have sort of the back or the heights of triangles, and then we have bases. So let's take a ratio of bases. So we could say this is base 2 and base 1. So if we take a ratio of the bases, and we're going to get 4/3. Now, because these are similar, the ratios of the backs should also be the same. So if I call this back 2, this is back 1. If we take the ratios of these backs, well, they're going to reduce down to the same fraction, 4/3. So because these are similar, that's what we're going to get. Now, any questions about that? All right. So let me do another one like this that just involves height.
At the top, you had the title going ratio of lengths of corresponding angles.
The corresponding sides.
Awesome, thank you.
And that does remind me, I do want to, I'll make a note a little bit later. I do want to mention angles with these. I'll get to that in a second. Basically, corresponding angles are going to be equal. But I'll mention that in a bit. For this next one,
I can't see the very top there.
oh, can you see this?
No.
Okay, let me fix that.
Thank you.
Oh, no problem. Is that better?
Looks great, thank you.
All right. So we're going to find the ratio of the corresponding heights. Now again, these are going to be similar triangles that should be mentioned. And these are not going to be drawn to scale. See if I can do a little bit about that. A little bit to scale. There we go. I try to have a little bit of realism. So let's say this height is 12 feet. And this height is 36 feet. Now, barring artistic license, suppose we can identify that this is the same corresponding side as this side. These are the same bases. Now, you got to be kind of careful with these triangles. You could tip one over, and if you did that, it might be kind of hard to tell if you're actually dealing with corresponding sides. Just because this side's sort of on the bottom and this side's on the bottom, that might not mean they're actually corresponding. One of these triangles could have been tipped over, so you want to be careful of that. Now, in this problem, we can make that assumption. I'm going to say that you can. That's okay. So this side is corresponding to this side. This side is corresponding to that side. And this side is corresponding to that side. And this height is corresponding to that height. So again, we're just going to take the ratio of the heights. And I'm going to use this format where the second triangle is the biggest triangle, the first triangle is the smallest. And so that's going to be your answer. Questions about that? All right. So let's say we have this. So I'm going to find side DE. And what DE is going to look like here. So this is what we've got. Now, again, these are supposed to be similar triangles. So this side is going to correspond to this side. This one's corresponding to this side. And this one corresponds to this side. So if we want, we could call this, say, like the inclines. We could call this the backs. And we can call these the base. Now we're looking for DE, and we have no idea what DE is. So let's give it some kind of identity, however vague. Let's call it X. Let's just recognize DE is a number. So how do we solve for X? Well, we have this rule that the ratios of corresponding sides are always the same. So if we take base 2, let me do, instead of using base, let's say this, side DE as our base 2. And this side, AB, this would be our base 1. Well, this is going to be equal to the ratio of another pair of corresponding sides. Well, what sides do we have available to make a ratio with? Well, we can't use these two sides because there aren't any numbers there. And we're not interested in these. We're only interested in that one. But we do have the two inclines, incline 2 and incline 1. So incline 2, we could call that side EF. Incline 1, call it side BC. So larger incline, smaller incline, larger incline, smaller incline. Larger base, smaller base, smaller base. So according to the rule with similar triangles, the ratios of corresponding sides, they're going to be equal. So that means the length of this base over the length of the smaller base equals the length of this incline over the smaller incline. And so that's going to be it. So now we got to solve for x. First off, any questions about that setup? All right. So we got to solve for x. So the way we can do this is what's called cross multiplication. So if we cross multiply, we're going to do this. What this means is we'll take 7 times x. And since I have a variable x here, I'm going to use the dot for multiplication so it's not confused. Equals 6 times 16. So we get 7x equals 96. Then we divide each side by 7. I'll grab a calculator for this. So what we're going to get, I'm going to round my answer to the nearest hundredth, or the second decimal place. I get about 13.71, approximate. So that's going to be my answer. Now, questions about that? All right. So let me pick out, let's see here. So let's say we have this one. So we're looking for the perimeter of triangle ABC. So let's say we have this. So this is what we have to go on. Now, if we want to come up with our corresponding sides, we can make this observation. Say this is base, base, back, back, incline, incline. So the ratios of the inclines, that would be DE, and I'm putting the larger one on top. You don't, again, have to do it that way, but if you do decide to go with the larger on top, it needs to always be on top. If you just go with the smaller on top, it needs to always be on top. So larger incline, smaller incline, larger back over smaller back. And then larger base, smaller base. Now, this is just the statement of the facts. We want to find the perimeter of triangle ABC. Now, perimeter means we need to add up all the sides. We're missing one of the sides. So the side we're missing, we're going to need it. Because we're interested in it, I'm going to call it X. So we're missing side BC. Because we're missing it, and we're looking for it, we need to make sure that this ratio is going to be involved. So what we're going to do, EF is 6, BC is X. Now, we want to work with a second ratio. We need one more. We don't have any information for DE. So DE and then the other incline, this isn't going to do us any good. The ratio of inclines won't help because we're missing this. But we could use the ratio of the bases. So FD is 8. CA is 4. So again, we're going to use cross multiplication. So 6 times 4 equals 8 times X, or 24 equals 8X. Divide by 8. We'll get 3 is equal to X. Well, that's part of our answer. Now, remember, we're not just looking for the side, we're looking for the perimeter. So let's go back to this triangle. So we just found out this is going to be 3 meters. So to find the perimeter, we got to add up all the sides. The perimeter is 3 meters plus 4 meters plus 5 meters, or 12 meters. And that's going to be our answer. All right, any questions about that?
Will you leave it for just an extra second so that I can copy it really fast?
Oh yes, absolutely, absolutely.
Thank you. Awesome. Thank you.
No problem. So let me do another version of these. It's an application one, and it works like this. So what we've got, let's say we have some sort of short tree growing next to a flagpole, kind of nearby. The sun's hitting them at the same angles for all intents and purposes, and they're going to cast shadows. This one's going to be 24 feet, this is going to be 8 feet. And you're able to measure the height of the tree. But you want to find the height of the flagpole. Now we don't know what that is, so I'm going to call this H. So what's happening here? When you're working with these shadows, you're actually getting similar triangles. So you have a large triangle, and then a smaller, similar version of it. So again, same shape, different sizes, barring artistic license. So that means the ratio of corresponding sides, those ratios are going to be the same. So this height over this will be equal to this base over this base. Or put another way, the ratio of the heights will equal the ratio of the bases. And if I'm going too fast, let me know. So, the way we deal with this. Again, you can use cross multiplication. And I'm just going to stick to the same technique. There are things you can do to simplify it, like you could sort of reduce this to 3/1 and then use cross multiplication to make things easier. I'm just going to stick to the same process. So I get 8 times H is 6 times 24. Or 8H equal, let's see, that's 120, 144. So now we got to solve for H. Again, since we're multiplying, we'll talk about this later in the algebra section. We'll do the opposite of multiplying, we'll divide. And 144 divided by 8 is 18. This is 18 feet. So this is kind of a neat trick. And granted, my triangles aren't drawn to appropriate dimension, but if you can, in a way, use this. If you know the height of something and the length of its shadow, and then you know the length of something that's way taller, or you don't know the height of it, but you know the length of its shadow, you can find the height of this thing. It's kind of a neat trick. So anyway, all right. So that's how that works. One of the application problems. So I do want to mention something because it could bring in a little bit of confusion, like, how do you know you're doing this right? And it's going to be this. So corresponding angles of similar triangles, those are going to be equal. Suppose these triangles are similar. And let's say they have angles A, B, C. And this one's going to have angle A, B, and I'll put a little curly Q on that capital C there. So what this says, angle A equals angle capital A. Angle B is angle capital B. Angle C equals angle capital C. And you're going to see this play out in the next example. Now this, we do have to make sure that we're dealing with some parallel lines in this next example. If the lines aren't parallel, this won't necessarily work. So any questions about this? So let me take a look at this next one. I'll draw the picture below. So just a little notation. These two lines here mean we have two line segments. This says that they're going to be parallel. So this segment will be parallel to this segment. I'm just going to draw the rest of it. So what this is saying is this and this. Here's DD, here's AE. These two are parallel. That's going to be important. Now BD is, let's see, 5 centimeters. AE, 8 centimeters. And then AC, 10 centimeters. I want to find the length of BC. So how the heck do we do this? Well, the thing we're going to do, we're going to look for a pair of similar triangles. It's going to go like this. Triangle CBD. And then the second one that's going to be our second. So we have this little one here. That's going to be our first. The entire one, that's going to be our second. Now the little one, BD, is 5 centimeters. And then this one, AE, is 8 centimeters. Now AC is 10 centimeters. And BC, we don't know. That's going to be X. So questions about this? All right. So one of the things you can make an observation of, this angle, well, it shows up here and here. Likewise, this angle is going to have the same measure as this angle. So you have the same incline, and it's cut by 2 parallel lines. Because they're parallel, the angle here and the angle here, they're going to be the same. So that's just something to kind of keep in mind. That's going to kind of help explain why these are similar triangles. Same thing with this angle and this angle. They're also going to be the same. So we're looking at some similar triangles here. So that means the solve for X, BC will take, say, the ratio of this over this. The ratio of this over that. Large over small, large over small. Now again, we're going to use cross multiplication. So we're going to get 8 times X equals 10 times 5. So that gives us 8x is equal to 50. Divide both sides by 8. We'll get x. Let's see, a good decimal for 50 divided by 8. Oh, perfect. It's already to the hundredths. 6.25. Let me look at our units here. What units did we have? centimeters. And so that's going to be our answer. Questions about that? So let me do another one. Let's see here. We're told that NO is 12 meters. MN that's 9 meters. Let's squeeze it in there. So this is 9 meters. This is 12 meters. PQ is 3 meters. And then oh dear, sorry, let me go Q here and P here. Switch these two, put P on top, Q on bottom. Okay, double check. Okay. So you got your P and your Q. And then from M to Q, 20 meters. All right. So what we're tasked to do is we want the perimeter OPQ, that triangle. So again, we're going to use similar triangles. And we actually have two similar triangles here. There's a large one. And a smaller one. We're going to rotate the smaller one. So P is on the 90-degree angle, so I'm going to put P here. Q is just across like that. And then we're going to have O right here. And then P and Q, that's 3. So the thing is, we're missing 2 sides on this triangle. How do we find them? Well, let's call them, say, X and Y. Now, first off, what we could do here is we could actually find Y. And the reason we can find Y right away is going to be this. We have information for the base. We're looking for a base. Information for the back, information of the back. So we can take the ratios of the backs and set that equal to the ratio of the base. So 9/3 equals 12 over y, the backs and the bases. So cross multiply. 9 times y is 3 times 12, or 9y is 36. Divide both sides by 9. We'll get y is equal to 4. So now we know what that base is on the smaller triangle. The tricky part now is going to be finding that incline. So to do that, I'm going to redraw. Now you already have this in your notes. I'm going to redraw. Oh, if I'm going too fast, let me know.
No, you're good.
All right. So I'm going to redraw this. So I'm going to show you sort of a trick. And so we found out that, let's see, they told us that MN was 9. This was 12. This one was 3. And we found this one. This one was 4. We're missing this one. So if you want to redraw this, you can, certainly. Now, we're also told, though, that this whole thing here is 20. So there's a way we can do this, is that we can redraw these. Not really redraw them. I'm going to make kind of a note. If we're going to call this unknown incline x, we can call this part of the incline 20 minus x. So it's sort of like this. If we knew this was, say, 5, well then this, since the entire thing is 20, this piece is 20 minus 5. Now, we don't know what x is, so we're just going to call it 20 minus x. And oddly enough, if you add this plus this, negative x and x will cancel out. We'll leave you with the 20s. So now, using this little trick, we go back to our triangles. This incline, both inclines together are 20, but just this incline is 20 minus x. So, let's see. That was P, that was Q. And that's what we got. And so this one, we've called x. So what we're going to do, we're going to come up with an equation that uses the ratios of the inclines. So this is going to be okay because we're going to have only one variable. So let's take largest incline, smaller incline. So we get 20 minus x over x. And then we can compare this to any other pair of corresponding sides. We could do the backs, or we could do the bases. Well, let's use the backs. Largest back, smallest back. So largest incline, largest back, smallest back. And leave the units off. So again, we're going to cross multiply. Now this one's a little tricky, or trickier. This is 3 times the entire quantity, 20 minus x. And this is going to be 9 times x. Now, this is something called distribution, and we'll talk about it again in that algebra section. But you take the 3, you're going to multiply it or distribute it to the 20 and the x. Now, again, we'll talk about this in the algebra section, but we're going to try to cancel any addition or subtraction first. And we want all the x's on one side. So let's cancel a minus 3x by adding 3x. And again, what we do to one side, we have to do to the other. So -3, +3, combine those, you get 0. 60 with 0, if you're subtracting 0, it's still 0. If you're adding 0, well, if you're subtracting 0, it doesn't change anything. If you're adding 0, it doesn't change anything. So 60 is just there. But this becomes 12x. Now divide both sides by 12. Well, go figure. X is going to be 5 meters. So this isn't actually what they asked us to do. They wanted us to find the perimeter of this triangle. So looking at this little triangle, so to find the perimeter, again, we just add the sides. And this is going to be familiar, very familiar. We're going to get 12 meters. And that's actually the answer they're going to want. So any questions about that? All right. So there's 2 more things to mention in this section. Congruent triangles and then the Pythagorean theorem. So for congruent triangles, you have the same size and you have the same shape. Now for similar side triangles, we have the same shape, but we didn't have the same size. In this case, they're going to be exactly the same. So the measure of AB is the measure of DE. Measure of BC equals the measure EF. The measure of CA equals the measure of FD. This side equals this side. This side equals this side. This side equals this side. The corresponding sides are equal. Now, here's a property. I want to have a warning on this property. Let me see. Well, I'll make this. I'm not going to put a warning, but also angle A equals angle D. Angle B equals angle E. Angle C equals angle F. The corresponding angles are equal. Excuse me, sorry.
Bless you.
Thank you. So the corresponding sides are equal and the corresponding angles are equal. You got to be careful with this one in particular, though. So I'm going to make a warning here. The warning's going to be this. Oh, and if you don't mind, if you could just turn off your camera and your microphone. Oh, perfect. All right. You want to be careful with this. If only corresponding angles are equal. In other words, the corresponding sides might not be. If you have triangles where only the corresponding angles are equal, they could be similar triangles. Because remember, with similar triangles, the corresponding angles are also equal. So you could have something like this. That's 90 degrees, 30 degrees, 60 degrees, and 90, 30, 60. You could have something like this. It's not enough to have equal angles to give you congruent triangles. The sides also have to be the same lengths as well, or the corresponding sides. So here's an example where the angles are equal, but they're not congruent, they're only similar. Again, similar is same shape, different size. Congruent is same shape and the same size. All right. So the trick we're going to be dealing with congruent triangles, the issue is going to be this. Let's say we're not given all the information. like all the information about the angles and all the information about the sides, can we still figure out if some triangles are in fact congruent? Same shape, same size. So we're going to try to figure it out when we don't have access to all the measurements for the sides and all the measurements for the angles. So our first situation is side, side, side. Or you'll see it abbreviated as S, S, S. So let's say we have information about the sides and nothing about the angles. We have 0. Is this enough to say that the triangles are congruent? The answer is yes. If the corresponding sides are the same lengths, then the two triangles are congruent. And where this could be kind of helpful, you can have like a slightly tipped over version. So these two triangles are congruent. I'm going to use an abbreviation for a triangle, the shape of a triangle instead of the word. So if you have two triangles and the sides measure the same lengths, and barring again my artistic license, or what we call side, 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 then these are congruent. So the bases, same length, incline, same length, the backs, same length. These are congruent. So that's one way of doing this. So and let me switch this up. If you have, let me see here. If you have two corresponding sides and included angle, have the same measures. I'm going to give you an example of what this looks like. This one's a little tricky. So let's say I have a triangle that's 7, 4. So I'm going to highlight it like this. And there's an angle. We mean included. We mean in between. So here are two sides. Now, these aren't corresponding to each other. We need to get their corresponding sides over here. So what we can do, and I'll put some label the points here. This is A, B, this is C, and then this one we'll call C. That's going to be F, E, D. So we can call this a base. And so the base of this triangle is going to be, it looks like it's going to be here. And these two bases, they have the same measure, those corresponding sides. And so we have also a back, and this is the back here, or at least if we rotated this triangle around. And so these also have the same measure. So we have a 4 and a 4, a 7 and a 7. We want to look at the angle now between these two sides and these two sides. If the angles are the same, then this will be corresponding. I'm sorry, congruent. So 120, 120, it does work. So that means triangle ABC and triangle DEF are congruent. They're the same shape and the same size. It's one of them got knocked over. When we talk about these two sides corresponds to this, corresponds to that. And then we have the angle in between. And so that's the idea of side, angle, side. Any questions about that? I kind of like the definition they give in the book. So let me give that to you for this one. I think it's clear. If two sides and included angle of one triangle are equal, in measure, to two sides and included angle of the other triangle. I just think that's just clearer. The other one, yeah, I think this one's a little clearer. Any questions about that? All right. Last one. Okay. angle, side, angle. And again, I'm going to use the book definition on this one. So two angles and the included side of one triangle are equal in measure to two angles and the included side of the other triangle. So two angles and the included side of one triangle are equal in measure to two angles and the included side of the other triangle. So what we did last time is we had an angle sandwiched between two sides. Now we're going to have a side sandwiched between two angles. So what this would look like, and again, included is going to mean between. So there are the corresponding sides. Well, not even corresponding, just the side and the angles. You don't have to really worry about corresponding. So the idea is this. We have two angles and a side that's between, two angles and a side between. This angle and this angle are equal. This angle and this angle are equal. Here, let me give you some labels there. D, E, and F. So angle, angle, equal. Okay, we got one a pair of angles equal. So far, so good. This angle and this angle are equal. So another pair of angles are equal. Now the side between them. So the side between these two angles is 9. The side between the two equal, or these two angles, also 9. So these two are equal, these two are equal. The side between both of those, both sets, that side is also equal. So this means by angle side angle, these triangles are congruent. Questions about that? All right. So the last thing to mention today It's what's called the Pythagorean theorem. I'm going to abbreviate theorem. This applies to right triangles. So a right triangle, and this is something we mentioned a while ago, so it might have been, might have easily forgotten. Right triangle has a 90-degree angle in it. Let's say that we have sides, A, B, and C. Well, according to the Pythagorean theorem, the side that's always across from the 90-degree angle, it has a relationship to the other sides. I'll give you the sort of the standard way this is presented. This is only for a right triangle. The side across from the 90-degree angle, if you square it, it's equal to the sum of the squares of the other two sides, or a squared plus b squared equals c squared. So for example, so let's say we're supposed to find x. Well, x, since it's across from this angle, we're going to square it, and it's equal to this side squared plus the other side squared. Or, stick to the formula a little bit more. Say 8 squared plus 6 squared is x squared. Now 8 squared is 64. 6 squared is 6 times 6, or 36. That's x squared. 64 plus 36 is 100. So the way you find this, you have to do what's called a square root. Now we haven't talked about exponents yet, so I just want to mention 8 squared is 8 times 8. 6 squared is 6 times 6. X squared is x times x. So if it's been a while since you've done exponents, this is something just to keep in mind. Now to get rid of a square, the way we do it, you have to use something called a square root. And so the way we handle this in the algebra, we're going to take what's called the positive square root. We're going to square root both sides. And it turns out that the square root and the square cancel each other. The square root and the square are going to cancel each other, provided x squared is by itself. If x squared is by itself. Now on your calculator, you do have a square root sign. So like on my calculator, I'll type in 100, and then there's the square root sign. So I'm going to press the square root button. I get 10. So 10 is equal to x. And that's going to be our answer. So one more example, and then that'll be it for today. Let's say we have this. Let's say you got to solve for x. Well, in this case, 20 is across from here. So that means x squared plus 16 squared equals 20 squared. Let's see, 16 squared, that's 16 times 16, or 256. So x squared plus 256 is equal to, let's see, 400. Yeah. So we need to solve for x squared. So let us solve for x. We want to get x squared by itself. It has to be by itself first. Subtract 256 from both sides. Well, plus 56 minus 56, those are going to cancel out. They're going to go away. That'll just leave us x squared. But what we do to one side, we always have to do to the other. So 400 minus 256, 144. So now we're going to take the square root of both sides. And then the square root and the square, they always cancel, leaving just x. And then again on your calculator, type in 144, square root, you'll get 12. And that's going to be our answer. So that's it for 7.4. If you have any questions about this section, let me know. I'll be checking the messages, and if you have any questions, give me a holler. Other than that, have a wonderful day.
Thank you.
No problem.